You are listening to The Vocal Technologist. Spoken tech for your ears.
Usually when we talk about engineering, there's this expectation of just absolute precision.
Oh, sure, like building a bridge, right.
Exactly. You calculate the load, you lay the steel, and you can, mathematically prove the bridge is going to hold the weight. It's entirely deterministic.
Yeah, but then you step into the world of modern data engineering and AI operations.
And suddenly you realize that bridge is moving while you're standing on it.
Exactly. We are looking at an infrastructure landscape that is just completely fluid, full of hidden variables, and constantly shifting under our feet.
Right. I mean, we're working with systems that guess, models that hallucinate, and data pipelines processing like millions of events a second, where the real cost is often completely invisible until you actually get the bill.
Yeah, the traditional rules of engineering precision just don't apply when the raw material you're building with is inherently probabilistic.
So true.
If you are listening to this, you likely already know the anxiety of deploying an update when you can't see the entire blast radius. You are effectively working in the dark, building systems that have to survive when their own internal predictions inevitably turn out to be wrong.
Welcome to our deep dive. Today we are digging into an incredible stack of dispatches from the front lines of data and AI engineering, all published in May 2026.
It's a really fascinating batch of sources.
It really is. And our mission today is to explore this messy, fascinating reality. We're looking at how the biggest tech teams in the world actually put data and AI into production safely.
Right, how they tame all this uncertainty.
Exactly. How do they prevent catastrophic crashes when the scale is this massive and, construct AI agents that are actually reliable enough to trust with production systems? Okay, let's unpack this. We're starting right at the foundation.
Yeah.
The illusion of certainty.
Because if your foundation is built on the assumption that a data model gives you a crystal clear picture of reality, you are architecting a failure right out of the gate. Across all these sources, we are seeing a massive shift in philosophy. The industry is moving away from trying to perfectly predict the world and moving toward building guardrails for when the models fail.
I saw this explicitly in the piece we have on scenario modeling for the English local elections. And just to be clear, we are just looking at the data methodology here, not taking any political sides.
Right, purely the engineering perspective.
Exactly. So the authors make a structural argument that really changes how you view forecasting. They argue scenario models need to be treated as data products, not as predictions.
And that makes total sense if you've ever tried to forecast anything complex. People obsess over the point forecast, right? They want that single comforting number.
Oh, totally. But the noise in these models, like the uncertainty band, that can actually be larger than the surprise shock event you were trying to detect in the first place.
Which is why point forecasts are actively misleading for exactly that reason. The engineers building these election models, they prioritize the guardrails.
What does that look like in practice?
Well, they version their assumptions as code, they freeze the model artifacts to create an immutable audit trail, and most importantly, they store their residuals.
The residuals.
Yeah, they meticulously track the delta between what the model predicted and what reality actually delivered. By exposing those uncertainty bands to the end user, they are essentially planning the post-event audit before the event even happens.
It's like relying on a weather app that guarantees it will be exactly 72.5 degrees at 3:00 p.m. That level of precision is just an illusion.
Yeah, a dangerous one.
What you really need is the radar view showing you the massive, unpredictable storm system of uncertainty rolling in. You don't need a guarantee, you need an umbrella.
That's a great way to put it.
And this concept of hidden realities isn't just about human behavior in elections. It's built into the very platforms we use to process this data. Let's look at Google BigQuery for a second.
Oh, this is a classic example.
Right. If you've ever optimized a query to get your cloud bill down, you probably looked at byte scanned. But the sources reveal that metric is essentially a smokescreen for the true architectural cost, which is the shuffle.
Yeah, the shuffle is the silent killer of distributed query performance. When BigQuery executes a query, it isn't reading a file top to bottom on a single machine.
It's way more fragmented than that.
Exactly. It is running parallel stages across thousands of workers, called slots. If your query includes a hash join, where you are joining two massive tables on a specific key, the system physically cannot compute that locally.
Because it doesn't have all the pieces.
Right. It has to take every matching key, hash it, and redistribute all that data across the network to matching slots.
Okay, right. Because all the rows with, say, customer A need to end up on the exact same physical node to be joined together.
You got it.
So you might scan a tiny amount of actual storage bytes. But if those keys are heavily skewed, like, say, one massive enterprise client makes up 80% of your traffic, you are forcing the system to rapidly pass mountains of data back and forth between thousands of nodes over the network.
And that network I/O becomes the massive bottleneck.
But wait, I have to push back on the platform design here. If BigQuery abstracts away the real cost of the shuffle and just shows you bytes scanned on the front end, aren't they structurally incentivizing data analysts to write horribly inefficient queries?
It's the classic trade-off for democratization, honestly. Cloud providers want analysts to write standard SQL without needing a background in distributed systems architecture.
Ignorance is bliss until the bill arrives.
Exactly. For the data engineers actually maintaining the infrastructure, relying on that abstraction is financially dangerous. You have to bypass the basic metrics and dig into the execution details panel.
And what are they looking for there?
That is where you uncover the stage-level compute time and compare the maximum versus average slot time. If your max slot time is 10 times higher than your average, you have a severe data skew problem.
Oh, so one node is just choking on that giant enterprise client while the rest sit idle.
Bingo. The byte scanned is merely the entry fee, but the network shuffle is what actually drains the budget.
That structural reality leads directly to our next major theme. If our models are full of massive uncertainty bands and our fundamental database queries have all these hidden, volatile execution costs, pushing updates to production is inherently terrifying.
It really is. Staging environments never perfectly replicate the sheer chaos and volume of production traffic.
So how do companies actually ship updates without breaking everything?
By running tests entirely in the shadows.
I want to look at Grab's data streaming team here because their solution to this is just fascinating. They run Apache Flink, which processes massive, continuous streams of real-time data.
Right, high-stakes streaming.
Yeah, and when a bad update made it into production, the rollback was causing a 10-minute downtime. In a high-volume streaming environment, 10 minutes of dropped data is a massive incident.
Oh, it's a disaster.
So they implemented shadow testing to eliminate that rollback window entirely.
And the architecture behind a shadow test in a streaming environment, it requires strict isolation. Instead of doing a typical blue-green deployment or swapping the old job for the new one, they deploy the new code as a shadow job running simultaneously alongside the production job.
So they're both ingesting the exact same live Kafka stream.
Exactly. And to prevent catastrophic interference, they use entirely distinct consumer groups.
Okay. For you listening, if you work with Kafka, you know that if two jobs share a consumer group, they start stealing messages from each other and messing up the offset tracking.
Right, which would ruin the test and production.
By giving the shadow job its own consumer group, it tracks its own place in the stream. It's exactly like having a stunt double run through a dangerous obstacle course right beside you on a separate, identical track.
I love that analogy.
If the stunt double falls into a trap, it doesn't slow you down at all, but you get to see exactly where the trap is.
Taking that stunt double analogy a step further, the shadow job also requires an isolated destination. It writes to a dummy sink, completely separate from the production database.
So it's not corrupting real user data.
Precisely. Because it is processing real, volatile production data in real time, the engineers can monitor its memory usage, back pressure, and output accuracy under true load.
And if it survives the gauntlet,
They promote it. If it fails, they just kill the shadow job. Zero downtime, zero impact on the end user.
wow. Now take that concept of extreme safety and apply it to the underlying infrastructure itself. Discord manages mind-boggling amounts of stateful data using ScyllaDB.
Massive scale there.
Yeah. And to orchestrate these complex clusters, they custom-built their own automation framework called the Scylla Control Plane, or SCP. I noticed they decided to build this entirely from scratch in Rust, using declarative YAML workflows.
Which is a very deliberate choice.
It makes total sense when you think about the nature of stateful databases. If a stateless web server crashes, a load balancer just reroutes traffic. Who cares, right?
Right, stateless is easy.
But if a database node goes down at the exact wrong microsecond during a rolling restart, or if a cluster expansion pauses unpredictably, you corrupt the data state. You need an ultra-safe language like Rust, because it guarantees memory safety without relying on a garbage collector.
Because you really can't afford random garbage collection pauses when you are orchestrating database nodes.
Exactly.
If we connect this to the bigger picture of deployment speed, safety frameworks like SCP are what actually unlock velocity. Alongside Rust's memory predictability, Discord designed every operational task in SCP to be strictly declarative and idempotent.
Idempotent meaning you can run it multiple times safely.
Exactly. If a network packet drops during an operation and the orchestrator triggers the YAML workflow a second time, an idempotent system doesn't blindly execute a second restart.
It checks itself first.
Right. It simply evaluates the current state, recognizes the target state has been met, and safely halts.
So by mathematically guaranteeing the safety conditions, knowing the cluster won't tear itself apart if a script runs twice, they remove the fear of deployment.
They can now execute rolling restarts and stand up completely new shadow clusters in under 2 hours rather than weeks of manual verification.
That is incredible.
That elimination of fear is the core tenet of modern infrastructure.
Here's where it gets really interesting. We've established how much effort it takes to safely manage data pipelines and infrastructure with strict, predictable guardrails.
Right.
But the entire industry is currently rushing to hand the controls of these systems over to AI agents. We are trying to move from mathematically predictable pipelines to autonomous, probabilistic reasoning engines.
Which sounds terrifying when you put it like that.
It does. And just like traditional pipelines, agents need strict guardrails to fail gracefully. But the way we've been building them might be completely backwards.
Yeah, the engineering team at Wix recently published an evaluation that really highlights this structural flaw. They ran 250 different evaluations on AI agents performing developer tasks.
What were they trying to figure out?
The goal was to settle a major architectural debate. When you give an AI an operational task, is it better to equip it with skills, which are basically hard-coded, predefined functions tailored for the agent to execute? Or is it better to just provide the docs, the raw API documentation, and let the AI figure out how to structure the requests dynamically?
Wait, aren't AI skills supposed to be the ultimate upgrade? It feels backwards that boring old documentation is sometimes the safer bet for an advanced AI. You would naturally assume the purpose-built skills would win.
You would think so. But the Wix evals proved that hard-coded skills are incredibly brittle. Sure, skills win on token usage and speed because the AI doesn't have to spend compute cycles reading a manual.
Right, it just fires the prepackaged function.
Exactly. But the moment the underlying API changes, say an endpoint parameter changes from useRid to accounted, the skill becomes stale.
Oh, I see.
The AI agent completely breaks down because it blindly pushes a button that isn't wired correctly anymore. It lacks the context to recover.
What if it has the docs?
Exactly. Providing the agent with optimized, up-to-date documentation acts as a much more resilient foundation. When an API changes, the docs are updated. The agent reads the current state of the system, recognizes the schema change, and reasons its way to a successful API call.
So it trades a slight increase in token cost for a massive increase in dynamic adaptability,
Spot on.
which perfectly aligns with the broader industry roadmap for tool calling. The sources point out that most AI agent failures don't actually happen because the large language model is stupid or fails to reason correctly.
Right, the reasoning engine itself is fine.
The failures almost always happen in the tool layer, the interface where the AI actually touches the software.
This is a critical insight for anyone integrating AI into their workflows. You cannot just hand an AI a generic tool and expect magic. Tools require precise definitions that act as strict, enforceable contracts between the AI and the system.
And you need rigorous, structured error handling too, right?
Absolutely. If an AI agent passes a string into an API that requires an integer, the tool layer cannot just throw a fatal exception and crash the loop.
Right, the AI wouldn't know what to do with a generic stack trace.
Right, it must catch the error, format it into a structured message explaining the schema violation, and pass it back to the agent so the AI can correct its own mistake.
You are basically building a software circuit breaker for the AI's logic. If you've ever tried to have an AI run a local script and watched it hallucinate a library that doesn't exist, this is exactly what's missing.
Yep.
You also have to tightly constrain the tool catalog size. If you give an AI 500 different tools to choose from, you dramatically increase the surface area for hallucination.
Restricting the agent's options is just as important as empowering it.
So to give these AI agents the right context, whether it's reliable documentation or strict tool contracts, traditional databases are clearly not cutting it.
Not at all.
The foundational data layer is mutating rapidly to support this AI-driven reality. To supercharge data for these architectures, the industry is moving away from flat storage and toward heavily connected contextual structures.
The transition from vector search to GraphRAG, which is graph retrieval augmented generation, is a perfect example of this. Up until recently, most enterprise AI relied on basic vector databases.
Right, turning text into embeddings.
Yeah, you turn your corporate documents into mathematical embeddings, the user asks a question, and the system retrieves text that is mathematically similar. But vector search is shallow. It doesn't really understand your underlying business logic.
GraphRAG changes that by explicitly mapping out the relationships between your data products. Traditional data catalogs are great if a human needs to find a table, but they stop there.
Exactly.
GraphRAG maps the entities, the business objectives, the KPIs, and the lineage. If you ask an AI, why is our supply chain KPI dropping? A vector database might just pull up a random Q3 PDF that mentions the word supply chain.
Which isn't very helpful.
Right, but a GraphRAG system understands the topology of the business. It knows the specific snowflake table generating that KPI. It knows the DBT model that transformed it, and it knows the Slack channel of the data engineer who pushed a code commit to that pipeline yesterday.
GraphRAG provides machine-readable business context. It represents data as nodes and edges, allowing the AI to traverse the logical relationships.
GraphRAG sounds like giving the AI a fully connected, interactive subway map of your entire corporate structure, rather than just handing it a massive phone book and telling it to look up a keyword.
That's a perfect way to visualize it.
Catalogs organize the portfolio, but graphs connect it, which is what allows the AI to actually reason across multiple hops of logic. And once the AI can deeply reason across the data, it can start to manage the data generation itself.
Right.
This brings us to Meta's Autodata system. Meta is using an AI agent to generate and critique its own synthetic training data.
It's an impressive setup.
Yeah, they built a two-loop agentic workflow. In the first loop, the agent generates candidate data records. In the second loop, a critique model evaluates that data against strict constraints, identifying flaws and forcing the generator to refine its output.
A self-correcting system.
Exactly. By letting the AI iteratively check its own work in this loop, Meta raised their validation pass rate from 12.8% to 42.4%. They are deliberately trading inference compute, letting the AI run longer in exchange for massively higher data quality without requiring a human in the loop.
What's fascinating here is the underlying infrastructure required to make those iterative loops fast enough to actually be viable in production.
Right, because that sounds slow.
It can be. The bottleneck for autonomous AI often isn't the reasoning, it's the sheer speed of data access. Look at the dispatch from NetEase Games. They were trying to implement serverless GPU auto-scaling for large language models.
And they ran into a wall.
A massive one. When a huge LLM boots up from a cold start, it has to pull hundreds of gigabytes of model weights from remote storage into GPU memory. NetEase was seeing cold start times of 42 minutes.
Wow.
That latency destroys the viability of any responsive agentic workflow.
Right. I mean, if my automated data scientist takes 35 minutes just to wake up and load its brain into memory, the task is already irrelevant. So how did they fix it?
They completely rewired the storage layer to prioritize data proximity. They implemented Alexio caching, which physically moves the data closer to the compute nodes, dropping the start time down to 14 minutes.
Still a bit slow, but much better.
But they didn't stop there. They integrated fully tuned fluid prefetching. Instead of waiting for the model to request the weights, the system analyzes the workload patterns, anticipates which chunks of memory the LLM will need next, and loads them into the namespace ahead of time.
Oh, that's smart.
By combining caching and predictive prefetching, they cut that 42-minute cold start down to under 30 seconds.
Under 30 seconds from 42 minutes. That is a staggering optimization. And we are seeing this hyper-optimization fundamentally reshape the entire stack to support AI workloads.
Absolutely.
Take HelixDB, for example. It's an emerging open-source Rust database specifically designed for AI applications. Instead of forcing developers to stitch together a graph database, a vector database, and a relational database, HelixDB combines all of them into one type-safe environment.
Which is huge for performance.
Yeah, it handles complex, disjointed reads across graph relationships and vector embeddings within a single Rust memory space, completely eliminating the latency of passing data between different specialized platforms.
We also see tools like Flowfile modernizing the data engineering workflow itself. Flowfile brings visual drag-and-drop ETL capabilities to high-performance Polars workflows.
And the reason that matters is that it democratizes data pipeline creation without creating vendor lock-in. Historically, visual ETL tools generated proprietary code that trapped you in their ecosystem.
Right, the classic vendor trap.
Yeah, but Flowfile allows analysts to build visually, but under the hood, it generates optimized standard abstract syntax trees that execute in polars. You get the accessibility of a GUI with the blistering speed of a Rust-based data frame library.
It's all about navigating this chaotic ecosystem efficiently, which is exactly why the data landscape interactive map was highlighted in these dispatches.
Yes. For you listening, if you are feeling overwhelmed by the sheer volume of new standards, vector databases, and AI tooling, the Data Landscape Project provides an interactive, community-driven map of the entire data ecosystem.
Highly recommend checking that out.
It categorizes the tools and shows how they interlock, which is invaluable when you are trying to design a modern architecture without accidentally relying on an obsolete standard. We're even seeing legacy disciplines like geospatial data being treated as foundational AI context, with extensions like PostGIS for PostgreSQL becoming standard requirements for AI applications that need to reason about physical locations.
But perhaps the most profound example of architectural optimization from all the sources is the move away from traditional databases entirely for certain static workloads. One engineering team managed to replace a 3 gigabyte SQLite database with a 10 megabyte FST binary.
Wait, really? A finite state transducer going from 3 gigabytes down to 10 megabytes is wild.
It's incredible.
For context, an FST isn't a database engine. It's a mathematically rigid data structure. It operates like a directed acyclic graph, where the paths themselves encode the data.
Right, so it's a completely different paradigm.
Exactly. Instead of storing discrete rows that a query engine has to parse and search, an FST maps keys to outputs at compile time. If your workload is incredibly narrow, completely predictable, and relatively static like a read-only dictionary for an AI tool, you don't need the massive overhead of a dynamic database engine like SQLite,
You just compile the data into an FST.
which fundamentally crushes the storage footprint while providing near instantaneous read speeds. It perfectly encapsulates the theme of all these dispatches. You must align your architecture perfectly to the physical reality of the workload. So what does this all mean? We've covered a massive amount of ground today, spanning everything from the scenario modeling of UK elections to the compile time mechanics of FST binaries.
If we synthesize all of these dispatches, the ultimate takeaway for anyone working in tech right now is a fundamental shift in engineering priorities.
How so?
Well, whether you are managing the uncertainty bands of an English local election model, orchestrating a massive ScyllaDB cluster using idempotent Rust workflows, or deploying an autonomous AI agent to write synthetic data, the goal is no longer perfect prediction.
Right.
The goal is not frictionless, unconstrained reasoning. The singular goal is building resilient systems. It's about structurally accepting that the model will be wrong, the deployment will drop packets, and the AI will hallucinate.
It's inevitable.
Exactly. Therefore, your architecture must be defined by isolated shadow testing, robust software circuit breakers, explicit data contracts, and mapped semantic relationships.
Which leaves us with a really fascinating question. The industry spends billions of dollars and endless compute cycles obsessing over making AI smarter. We are constantly pushing the parameter count higher, trying to make the raw reasoning engine faster and more capable.
Always chasing the bigger brain.
Right. But based on everything we've looked at today, from Grab shadow testing to Wix's highly structured tool contracts to the beautifully connected subway map of GraphRAG, what if the real secret to the future of AI isn't about building a better brain at all? What if the real secret is simply building a safer, more heavily guarded playground for that brain to make mistakes in?
I think the evidence strongly suggests that is exactly where the most successful engineering teams are focusing their efforts right now.
It's definitely something to think about the next time you ask an AI to run a script for you. Thank you for joining us on this deep dive. Keep questioning the metrics, keep exploring the architecture, and we will catch you on the next one.
Spoken Tech for your ears.